Today I would like to talk about how the Bitcoin protocol actually works. So my name is Møller. I'm working for a company called Mycelium in Austria, out of Denmark. We are making Android apps and other interesting stuff for sending and receiving Bitcoin. But that's not what I want to talk about today. Today I want to talk about how the Bitcoin protocol actually works. So this talk is not about the political environment around Bitcoin or economics. It's not about how you buy and sell and speculate in Bitcoin. It's more about how the Bitcoin protocol actually works. So into the technical stuff, this is where I belong. So this talk is pretty compacted because kind of the first 3 times you think you understand Bitcoin, you are probably wrong. It is really complicated, and I'm trying to put that into like 45 minutes. And my hope is that after this presentation, you will only think like 2 more times that you are understand it, and you don't. So, okay. So, but let's start with the beginning. So, how did it actually start? Well, in November 2008, Satoshi Nakamoto published a white paper to a mailing list about cryptography. And on that mailing list, a lot of crypto stuff was discussed. And one of the things that have kind of eluded them for a long time is, how can you actually make something that is totally decentralized and at the same time is a payment system without any central authorities and things like that. So this has kind of been the holy grail for many years. And along comes this guy, nobody heard of him before, and he said, well, here's the solution. And it was not really received well because people they said that, come on, this nobody cannot just come along and solve this, right? But he did, and it took some time. Like 3 months later, he made an implementation, an open source implementation that everybody could look into, and the network started at that point. Now, an interesting thing is that nobody knows who Satoshi Nakamoto is. It can be a man or a woman or a group of people. Nobody knows. He has remained anonymous since the very beginning. And sometime in 2010, he disappeared. We haven't heard from him evermore. So, and that's kind of also a little bit interesting. But the thing is that at that point in time, enough people had jumped onto this open source project and had evolved it, and he was not really needed anymore. And he may have had some reasons for being anonymous, because Bitcoin is a very disruptive technology. It will, if it really succeeds, it will probably redefine the way we think money and a lot of other factors. But this is the way it is. Okay, but what is Bitcoin then? Well, Bitcoin is the name of a protocol, a peer-to-peer protocol that governs the rules of the network. So all the nodes in the network, they adhere to these rules and enforce them. Okay, Bitcoin is also a unit of account. So just like you have euro, Danish kroner, or World of Warcraft gold coins, it's something that I can have like 10 Bitcoins and I can give them to somebody else. It's a unit of account. And the giving coins to somebody else is what makes Bitcoin a payment system also. So it's a system that allows people to send value between accounts. Okay, so, well, don't we have something like this already? And, well, to some extent we do. So if we look at common digital payment systems, we have, like, in Denmark we have Dankort, internationally we have Visa, or in World of Warcraft we have gold coins. And, with all these systems, there are some properties. I selected a few here, like you can't increase the money supply at will. So I cannot produce more Danish kroner in my Dankort. It's simply not part of the rules, right? I cannot double spend, so if I have a bag of gold coins in World of Warcraft, I cannot both buy a shield and then a sword for the same bag of coins. Another thing, transactions irreversibility, is that I cannot undo a transaction. So once I bought the sword, I cannot kind of go back unless I make an agreement with the guy who I bought it from. So this is what we have in common digital payment systems, and it works pretty well, except that, and here I've put emphasis on you, because You can't increase the money supply at will, but somebody can, because these certain systems are centralized. So somebody at the Danish National Bank can start the printing press and, produce more money. Or World of Warcraft, they can say, well, all of a sudden all the monsters give like 2x the amount of gold, and then all of a sudden the rules, they change. So I can't do counterfeiting, but the system can because it's centralized. And the same thing with double spending. So I can't spend the same money twice, but others in the system can. Like for instance, the Danish banks, they can, if I give them 1,000 kroners, they can then lend out 900 kroners to two different people based on my money. It's called fractional reserve banking, and it happens all the time, and it's part of how we increase the money supply in Denmark and many other countries. And at the same time, transactions are irreversible with a Visa card, but if I'm a merchant and somebody comes and buys a pair of shoes from me, then if it turns out that this credit card was stolen, then Visa, they can reverse the transaction and take the money right out of my bank account. So that's not really that great. So if we compare this to Bitcoin and look at the properties of Bitcoin, well, then we also have no counterfeiting, but nobody can increase the money supply at will. There's no central server that governs the rules. It's all distributed, so you just can't do that. Another thing, transactions are really irreversible. Nobody can undo a transaction. And you should take that with a grain of salt, because at the very tip of things, funny stuff happens, but we will get into that. And also double spending, so nobody can spend the same value twice. It's just not possible. Okay, so basically, Bitcoin solves at least two things. At least those are the ones I want to focus on here. So it eliminates trust in a central authority. There's no central place that kind of is the truth of all things. It's the network. So you trust the rules of a protocol, and they are enforced by mathematics and cryptography. Another thing is that Bitcoin solves the distribution of funds problem. Because if you make a new currency, who should have all the value in the very beginning? So if Satoshi Nakamoto had all the Bitcoins in the beginning, and he could then kind of choose to dish them out randomly or by some other means, well, then you have a centralized system. So how do you create a system that does this in a decentralized way that everybody can trust? So this is what it's all about. So let's start with the funds distribution. So the way it works in Bitcoin is that every 10 minutes since the beginning of the network, a random node in the network receives a reward. Okay, sounds good. And that reward started at 50 Bitcoins and halves every 4 years. So, okay, but how does it really work then? Because how can you enforce these things? How can you make sure that in a system where nobody trusts each other, that you can make something happen about every 10 minutes? And if you actually look at it, these two rules give a funny distribution here. So in the very beginning, 2009, 0 Bitcoins existed, and then gradually, every 10 minutes, 50 Bitcoins came into existence. And that continued for the 4 first years, and we reach about here. And half of the money is now in circulation. So random nodes in the network received 50 Bitcoins, and we have now distributed the money randomly, kind of. And we will get much more into that. And then, the next 25% of the monetary value is added over the next 4 years, and so forth. And as you can see, this graph converges on 21 million sometime out here in 2140. And at that point, there's no more coin distribution, and then it's kind of over. So this raises some questions. So first of all, 21 million. Are there only 21 million coins? Yes, there's never going to exist more than 21 million. That's the maximum. But how does it work? Like, we have 6-7 billion people in the world, so they cannot really all participate in this. Well, a Bitcoin can be split into very small fractions, like 1 Bitcoin can be 100 million small tiny pieces, so 0.00001 Bitcoin is what I can send into the network. So that's not really a problem. So, but how are these rules then enforced? And to understand that, we need to introduce the big invention in Bitcoin, the thing that is at the very core, the thing that didn't exist before 2008, so the new thing that we have. And this is the blockchain. So the blockchain is a database which contains all the transactions that ever occurred in the Bitcoin network. And it's like a public ledger where you can see everything that happened. So all the nodes in the network, they have a full copy of that blockchain. And they keep it up to date gradually as it increases and verifies that everything is sound. And some nodes in the network, they extend the blockchain, and they're called miners. And we will get a lot more into that. Okay, so blockchain, well, just like the name suggests, it's a chain of blocks, or a linked list, if you will. So basically, the blockchain contains a bunch of blocks, and they all point to a parent, which eventually points at the genesis block, so the very first block that was part of the software that was released. And the genesis block actually contains the title of a newspaper from the date that it was issued, so to make sure that it didn't exist before. So you can think of the blockchain as a big accounting book. Where you have debit and credit between accounts, red and black numbers going back and forth. And every page in that big accounting book is a block. And anybody can try to add a page to that block. And that's actually what happens roughly every 10 minutes. So anybody can go ahead and try to do that, but it's computationally hard to do so. In cryptography, there's something which is called a proof of work. So to do this, you have to prove that you have done a substantial amount of work, because otherwise it's too easy, and we will have too many blocks. So this is the problem we want to solve: how to make new blocks appear every 10 minutes on average. So to understand that, we need to go a little bit into cryptography and introduce SHA-256. So it's a commonly used cryptographically secure one-way hash function. And basically, it takes any size of input and produces exactly 32 bytes. And those 32 bytes are, practically speaking, random. So if you flip one bit in the input, then you get a totally different, randomly distributed output. So here's an example. Like if you take SHA-256 of GOTO, then you get this blob there. And if you take SHA-256 of to-go, then you get an entirely different blob. The important property of that function is that given any output, you cannot calculate the input. That's computationally unfeasible, unless you know the input, of course, first. So you cannot go back. All right, so this function is used when you want to mine blocks. So how to create a new block? Well, at any given time, we have from block 0 to block n, where n is like the tip of the blockchain. If you want to create a new block, then you create both a header and a payload. So the header contains a bunch of fields, and the payload contains the actual transactions, and we will get a lot more into that later. So the first thing to note here is that the header contains this previous block hash. So it contains a reference to the parent transaction that you want to build on top of. So in this case, we calculate the hash of the latest block and put it into our block header, and then we calculate the hash of our own header, which is basically just SHA-256 twice on the header. So you hash on those 80 bytes, and you're kind of done. But there's a small catch here, because this is trivially easy. Running SHA-256, you can do that millions of times a second on a computer. So there's a catch here. The block hash must be below the target difficulty. So in essence, this means that at any point in time, the network has decided what the current difficulty of the network is, and the block hash, when you regard it as an integer, it must be below a certain number. So here's an example. Here we have block 321,511, which was mined last week, and the block hash is this number. And you can notice here that there's a bunch of zeros in the beginning. So this is basically, there are 64 0 bits in the beginning of this hash value. And because SHA-256 produces a totally random output, it takes really many attempts to get to that hash value. So basically what you do is you create the header, then you notice in the header there's a nonce field, you put in a random value, then you calculate the hash of those 80 bytes. And if it's below the target, yay, we found a block, and we can collect our reward. If we didn't, then we go back to 2. And this happened a lot of times. So last week when I made those slides, the network had a hash rate of about 250 million gigahashes a second. So 1 gigahash is 1 billion hashes a second. So 250 million billion hashes a second was enough to create this block in 10 minutes. And that's a lot. So my computer at home with 4 cores can do like 2 gigahashes a second. So it's a high number. So basically, by having the right difficulty, the network can ensure that on average it takes 10 minutes to find a solution to this puzzle. And that's the proof of work that Bitcoin uses. So for this to really work, well, then we cannot have the difficulty to be a constant, because nodes are entering the network and exiting the network, and some of those nodes are mining, and some of them are not. It's not everybody who is looking for these puzzles, and therefore the difficulty adapts over time. So the way it works is that you see the red line here. This staircase thing is basically the difficulty observed over time. So what the network does is that every 2016 blocks, which is roughly 14 days, it looks at how long time did it take to calculate all the blocks, all those 2016 blocks. How long time did it take? And if it was too fast, then we increase the difficulty. If it was too easy, then we decrease the difficulty. And every node in the network calculates this difficulty simultaneously and reaches a result, and this is what we do for the next 14 days. So basically, the difficulty rises and declines over time, and this is the way that we ensure that blocks are found roughly every 10 minutes. Sometimes it takes a second, sometimes it takes an hour, but on average, 10 minutes. So now that I found this, let's say that I found this solution to this block, okay? And now I want to send it out into the network. So what happens is that all the nodes that are mining, they are then trying to look for the next block, and then they observe a solution. And there's one rule in the network, which is that the longest chain wins. So basically, when they see a result that and they can verify that it works, then they immediately discard whatever work they were doing because they want to be part of the longest chain. Because if you're working on a shorter chain, then you don't get this reward. So the reward is only for the winners, and the winners take it all. So, so since there can be more than one solution to a block, because it's basically just a random value that is below a number, there can be places where you have forks, where you have 2 solutions that appear at the same time. And if you take a look at this simplified version of a network where you have a bunch of nodes, and they are, let's just assume for simplicity that they are connected to the immediate neighbors. So if the guy down here finds a solution and he sends it out, well, then it takes some time for it to propagate in the network. And this is something it takes maybe seconds or I don't know, half a minute for everybody to see it, but that's actually a long time when you have new blocks every 10 minutes. So what happens if a guy in the other corner of the network finds a solution at the same time? So then you get something like this, where we have 2 different kind of futures. Part of the network saw this block up at the top first, and another part of the network saw the block at the top, at the bottom. And basically, you don't really know which chain is going to be the longest, but since you want the reward, you want to work at the thing that you think is going to be the longest chain. So basically, you just start working on the first block that you see, and then hope for the best. This kind of scenario happens pretty often, like a few times every day or something. So what happens? Well, you basically have the network separated in 2 camps, and they are all trying to beat each other. And eventually, one of the chains will have a new solution, and they will now have a longer chain. And everybody who observes this will immediately stop working on this other fork and then jump onto this problem, because there's an incentive to do so. Because if you don't, well, then you will have to first solve this block and then the next one before the reward ticks in. So this is a very condensed way of explaining Bitcoin mining and explaining coin distribution. There's a little bit more to Bitcoin mining when we get into transactions. We will talk about that in a minute. But this is basically how funds are distributed in the Bitcoin network. You can choose to go ahead and do this if you want, and you could choose not to. I've never personally mined. Well, I think I mined for a few hours at the very beginning, and then I figured out that you have to be very good with screwdrivers and stuff like that, and I'm not. So I decided making software instead. Okay, so this is distribution of funds, and now we move into how you make these transactions, which is what it's all about. So in Bitcoin, we use public-private key cryptography. So basically, just like with when you go to an HTTPS site, there we use RSA, and then we verify that the guy we're talking to is actually the one we want to talk to, and there we use RSA instead of Bitcoin elliptic curves, which Bitcoin uses. The reason why Bitcoin uses elliptic curves is because they are the signatures are shorter, so the blockchain will grow less when we have shorter proofs. So in Bitcoin, private keys are 32 bytes, and you can compute your public key from a private key using elliptic curve math. And there's no encryption in Bitcoin. Many people, they say, oh, cryptography must be encryption, but it isn't. It's just signing and verification of signatures. Okay, so and these private keys are very fundamental when you send transactions. But we have to introduce one more thing, which is Bitcoin addresses. So a Bitcoin address is just like a bank account. I can have some value in an address, and I can send value from an address to another account. They look like some gibberish, just like bank accounts do in the real world, and you can calculate them from a public key. So by doing 2 hash operations on a public key, you end up with a Bitcoin address. So you can have as many as you like, and basically because private keys are just random numbers, and believe me, 32 bytes of randomness is a huge, huge number. So there's enough for everybody for in the entire eternity. So you can have as many private keys as you want, which means you can have as many Bitcoin addresses as you want. And nobody really knows who owns which account. So all the transactions in the network are public. Everybody can see them, but nobody knows who owns what money if you have many addresses. So there is some degree of being anonymous in the Bitcoin network, but it's not perfectly anonymous like cash is. Okay, and so basically, value is moved between addresses using transactions. All right? So let's take a look at transactions. So this is a little bit simplified. A transaction has a bunch of inputs and outputs. It's just a stream of bytes with an interesting encoding. So in this example, I have 3 different inputs and 2 different outputs. So what happens here is that I send 5 Bitcoin from one address and 3 Bitcoin from another address and 4 Bitcoin from a third address, and I send them to 2 different addresses. So I have my inputs and my outputs, and this is basically what it looks like. A transaction also has a hash, which is basically SHA-256 of the raw transaction data, and this gives you a unique ID of a transaction. So there's more to it. So let's build it up a little bit slowly. So let's say that I want to send 10 Bitcoin to Troels, sitting right there. So what would I do? Well, I start by creating my transaction here with one output. Those are the 10 Bitcoins that I want to send to Troels. And I also add his Bitcoin address to this record. Very nice. Then I need to have some funding. I cannot just send money out of nothing. So I need some inputs from previous transactions that are sent to me. So I look in the blockchain for transactions that send some value to my addresses, and I find these 3 here. So at some point, somebody sent 5 Bitcoin to one of my addresses, and then also maybe a Bitcoin to somebody else. And same here, 3 Bitcoins to one of my addresses. It doesn't have to be the same. And then 4 Bitcoin. So now I have collected funding for my transaction. And if you add it together, you get something like 12 Bitcoin is my input. And then I have 10 Bitcoin as output. So in Bitcoin, you cannot spend some of these outputs partially. You have to spend it all. So basically now I have, a difference of 2 Bitcoin between my inputs and my outputs. So in order to fix that, I add a second output, which basically sends the remaining 2 Bitcoins back to myself. And that sounds a little bit odd, but it's just like when you go to the bakery and buy a bread. So I have a 50 kroner bill in my pocket, and the bread costs 30 kroner, so I get some money back. So I get these 20 kroners back, and it's actually the same thing that happens here. So I send 10 Bitcoins to Troels, and then I send 2 back to myself. And eventually I can spend those 2 Bitcoins in a transaction later on. So one more thing here is that if it was totally for free to send transactions in the Bitcoin network, then anybody could spam it with transactions that just send you money to yourself. You can, make hundreds or millions of those transactions. So therefore, there's a fee system built in, which basically means that I can leave a small goodie to the miners of the network and make them give my transaction priority. So the way it works is that if I subtract a tiny bit from this output to myself, then there's a difference between inputs and outputs. And that difference is the fee that I pay the miner. So in this scenario, I have 0.0001 Bitcoin. It's a very tiny amount, but it's something that the miner can see and can then choose to include my transaction in a block. And we will get back to fees in a minute. The thing is that I'm trying to explain 3 different things at the same time, and it only really makes sense when you get it all. Okay, so before I'm done, I need to prove that I own those coins. So what I do is that I take the private key that belongs to this Bitcoin address that received those 5 coins earlier. I take that private key, and then I sign the entire transaction and put the signature and the public key into the input. And of course, the input also has a reference to the transaction that it draws funds from. And I do that for every input. And once I'm done, I then broadcast this transaction into the network. And just like with the blocks, it then slowly propagates to all the nodes in the network, and it can take a little time. But eventually, all the nodes will see it. And that process is basically called transaction relaying. So when a node receives a transaction from some other peer, it funny music. Oh. So basically what it does is that it verifies that it is sound. So all the signatures, are they okay? All the inputs that this transaction is spending, are they really unspent? And verifies that that the outputs is no larger than the inputs. And there's a bunch of rules there. Once it has done this, it sends it on to its other peers. Eventually, all the nodes will see this transaction, and they have kind of a pool of unconfirmed transactions. So these are transactions that they have seen in the network, but they don't really know in which they are not really, we call it confirmed. They are not nobody really trusts them until they are really confirmed in the blockchain, because the blockchain gives you an ordering over time of events that have happened, basically. So the miner, when we go back to the miner now, the guy who got this reward for creating these blocks, well, he has this payload section down here. And basically he can pick and choose any transaction that he wants from this pool and put it into the block. When he does that, he calculates what is called a Møller root. A Møller root is basically a binary tree of SHA-256 hashes, which ends up in a 32-byte value, just like the block hash. So basically, he makes a choice of transactions that he wants to confirm. He calculates this Møller root and puts it into the header, and then he starts doing hashing and then finding a solution to this proof of work algorithm. And at some point, he will be done, and he will broadcast the entire thing to all the other nodes. And everybody will now recognize that, well, this transaction that I sent to trolls is among those down here, and now it has been confirmed by one miner, and it's put into the block, the first block. So, and that's a good thing, because then trolls has some belief in that, that this transaction is actually his. But the thing is that there can be forks in the network. And we saw that earlier with when we talked about distribution of funds. So let's just revisit it. So once in a while we have these forks. So basically there exist two alternate futures. One where my transaction has been confirmed, and one where it hasn't. And basically what happens now, because there are kind of two different scenarios. One scenario is that I'm an evil guy and I want to cheat trolls. And I can do that maybe by sending out two transactions, one which sends trolls the money and another one that sends it to me. So I can, in secret, create two transactions, send it out to everybody in the network, and half of the network will believe that one is the actual transaction, and another half will believe that the other one is the right one. So in that scenario, it really is a race of who puts it into a block first, right? So trolls cannot be really sure what happens. Another scenario is that I'm not really trying to cheat. I just want to be honest and send him some money. But we have this fork anyway. So in that scenario, my transaction will be in two different blocks, and that is happening actually several times a day. That the network forks, but the transactions are, well, if it's not included in one block, then a miner may put it in a block later on. So there could be a reason why this miner said that, well, I don't want to include Jan's transaction because he put a very low fee, and I don't want any free riders. But then another miner eventually can pick it up and put it into a block. So, and this is roughly how it works. And there are some, and there are more details to it. But this is kind of the depth that we can reach. But let me go back to the properties that I talked about earlier, because how does this system solve those properties? So we talked first about counterfeiting, that nobody can increase the money supply at will. And that's almost correct. So basically, you can only create money by solving this mathematical puzzle, right? And to do that, you have to prove that you have a lot of computation power. And basically, you are competing, when you're creating blocks, you're competing with the biggest distributed computer the world has seen. It's much faster than, actually I read a story or a paper on that a half a year ago, where it said that if you took the 500 biggest supercomputers in the world and added them together, they would be 200 times slower than the Bitcoin network at solving SHA-256, which is quite powerful. So if I really want to increase the money supply rapidly, I am forced to solving these blocks. And if I have more computing power than the rest of the network, I can maybe do that for a short period of time. But eventually, the difficulty will readjust so that it gets just harder for me, and I cannot, continue to do that. So maybe you can increase the money supply for a short period of time if you have really a lot of computing power, but you can't do it continuously. Okay, the next thing is transaction irreversibility. So nobody can undo a transaction. And that's also not the entire truth, because at the tip of the blockchain, bad stuff can happen. So here's, again, the example with trolls here, is that I created this transaction originally, and then, eventually a miner, he confirms it, and everything is good. We have a confirmation on the transaction. But maybe in secret, I have, created an alternate future where I have a longer chain which doesn't contain this transaction, but another one that spends the same outputs and send them to me. So in order to pull that off, again, I need more than 51% of the network's calculation power, which is not really possible. And if I really manage to pull it off, I invested millions of dollars into getting this computer gear. Well, then I would have cheated trolls of one transaction, and everybody would lose faith in the network, and maybe I wouldn't get that much out of it anyway, because I would just cheat him for some bitcoins. So this attack is very expensive. So the last property is no double spending. And so basically, all the nodes in the network continuously validate that the blocks are sound. So if a miner creates a block and it contains a transaction that has outputs that were spent previously, then the nodes will see that and then just throw it away. So you cannot do double spends unless you can reverse transactions, and that costs a lot of calculation power. So blockchain technology is very new. It has only been around for a few years. It started as in the grassroots, and it's getting bigger and bigger every day. And basically what it gives you is a trustless, decentralized ordering of events. So there's no central server, but somehow you can get an agreement of the events that happen in some certain order. And that is pretty powerful. It's a tool that we haven't seen before. And you can do lots of interesting stuff with it. One of the earliest examples is Namecoin. So it's a different currency called Namecoin with a different protocol, slightly different protocol, but still a network based on the same principles as Bitcoin. And basically that is a decentralized open source information registration and transfer system. So just like DNS, but just decentralized. So there's nobody who can come and say that Mads, you don't own Coke.com anymore. We give it to Coke Corporation instead, or something like that. So, but you can register basically key value pairs, and you can then transfer them to somebody else, and they can. And you can do that using Namecoin. So it has its own currency, and you can transfer stuff around. Other people are working on a solution where you can trade stocks, and you can have a publicly viewable record of who owns which stocks, and you cannot cheat, and there's no trading below the counter and stuff. Another thing is Votecoin. And I read an article actually in version 2, which is a Danish IT news site, where it said that Liberal Alliance, which is a party in Denmark, they have announced that they are in favor of blockchain-based voting. So if you do voting using the blockchain, then you virtually cannot cheat anymore, because everybody can count the ballots, because you can see in the blockchain all the transactions that occurred. Everybody can count who got how many votes and such. Very interesting stuff. Of course, it requires that people, they can manage their private keys, and that is tricky. So it's not a no-brainer, but very interesting. So interesting technology, and we can do stuff that we couldn't do before. So that's it. Any questions?
So how many transactions can there be in a block?
Yeah, so right now there's a rule in the network that says that a block can only be 1 megabyte large, which basically allows you to have around, 1,000 or something transactions in a block. And that is obviously not enough, because if we want this to really scale, then 1,000 transactions, in every 10 minutes is just not enough, right? So there's a lot of stuff to improve on. Yeah, tools.
Question from the audience. Why the separate Bitcoin addresses? Couldn't you just use the public key for addressing?
Yeah. So the question is, why do we have these Bitcoin addresses? Couldn't we just use those public keys? And we could. The thing is that public keys, they are larger. They are roughly 33 bytes when you kind of compress them. And the Bitcoin address is only 20 bytes. So there's something saved by doing that. And also there's another potential attack, which is using quantum computing. You can potentially in the future attack elliptic curves because of the mathematics involved. But quantum cryptography cannot really be used for brute forcing SHA-256 because it's a different kind of math. And that's also a reason. So a Bitcoin address is the hash of this public key. So it's two different classes of mathematics you apply. Yeah?
I have two questions. One being, what happens in the end when the benefits of doing mining ends?
Yeah, good question. So basically, we see this reward, it halves every 4 years, and eventually it ends up being zero, right? So and you cannot have Bitcoin without mining. So why should people continue to mine? So the thing is that right now the mining reward is based on the block reward, but there's another reward which are the transaction fees. So if I leave like 0.001, it might not sound like a lot, but if there are many transactions, then it adds up and gets to be something. And the idea is that gradually the miners will be living on the transaction fees instead of the block reward. So, and it will be, it will happen gradually over 100 years or something. So it's going to be interesting to see how it works out, because in the end, there's an incentive for the miner to add these transactions at any cost. Basically, any positive value should be enough. But on the other hand, there's also that when the blocks they increase in size, they take longer time to propagate over the network. So you might lose the race of sending the block out to everybody before another solution is found. So there's kind of some dynamics here, and eventually I think that there will be basically a market for transaction fees.
Yes. So what would be the reward in something like Dogecoin? Because they still also need a computing power.
Sure. And I'm not 100% sure how it works with Votecoin. I haven't looked into it in detail, but I could imagine that if there's a vote on something, that people they would be interested in just adding computer power just to ensure that the vote is done right. So if you are part of Liberal Alliance, for instance, then maybe you would volunteer your computing power to secure the Votecoin network while the vote lasts. As an example. Mess?
You said that the limit on number of transactions was not big enough, and that would have to change. Who changes that?
Yeah. So the question is, who changes Bitcoin? So basically, Bitcoin is open source. Anybody can download it and tear the code apart and do something funny and then start it, and it still works because the other nodes will not trust you. So, but how does the code actually change? So there's a list of core developers. It's about 10 people or something. And they have a very open process where any change is voted on. And basically, any core developer can say no to a change and then come with a reason, and then it has to be altered. Anybody can go in and see the change list. It's done on GitHub and verify that they're not messing around. And it's scrutinized a lot. There's a very big incentive to find security holes and whatnot in Bitcoin. It's several $1 billion of worth are put into Bitcoin in value, and if you can find a hole or something, then it's profitable. And many people have tried that. But there's a committee kind of that does this, and it's very, very open. So.
Yes. There were news recently that one organization was close to getting 51% of the network.
Yeah. So the question is, how about this news that came recently that an organization was close to getting 51% of the calculation power, and that is really bad. So basically, the way mining works today is that because you have very little chance of finding a block yourself, because the network is so big now, then people they have gone into what's called mining corporations, kind of. So you can take your mining power and add it to some a centralized system and say that I'll mine for you guys, and there are many of those. And the interesting thing is that if I do that, then there's a higher probability that this group finds this reward, right? So if I do it on myself, then it will maybe take 10 years before I find a block. But if I do it with them, we will find a block once in a while, and then we can split the profit. So that makes sense. But the problem was that one of these mining corporations got really big. And if they control 51% of the network, then it's bad because they can do bad stuff. So, but the thing is that they don't really, they only control this mining power on behalf of others, right? And these others, they can then say, oh, there's something bad here. I'll point my mining power at a different mining pool. But there was, I think at some point it was very close to 51%, and it is bad, and we have to solve that. And a lot of interesting solutions have come up with how to change that in some way, but it's complicated.
And there's no guarantee that they won't just enjoy the chance to get rich.
Who?
There's nothing guaranteeing that the people donating power to the corporations will say, I want out, this is bad. They might say, I want in, this is good.
Yeah. So, but the thing is that if you people who mine, they invest a lot of time and effort into mining. They buy racks of hardware and time and such. And if they are instrumental in damaging Bitcoin, then all of this investment will go away, right? So they are heavily invested into making Bitcoin a success. So and that's their incentive to actually say, oh, this is bad. I'll choose another mining pool because I want to secure the network.
I think you mentioned about the two possible futures where a transaction has happened and another it hasn't happened. So, and I hope you have mentioned it, but I'll get a chance, that how long should you then wait for confirmation that the transaction has taken place? Because, well,
So the question is, how many confirmations should a transaction have before you can say that it's really mine? So basically, the more blocks that your block is buried under, the more likely it is to remain there for time and ever. So in the very beginning, Satoshi Nakamoto said that, well, if you do the math and calculate stuff, then 6 confirmations, then you are very, very, very sure. But as it has evolved, the Bitcoin network is so strong today that just a few blocks makes it really unlikely that just a few I would but it really depends on the amount that right. So if Mads is sending me 100 kronos, then I wouldn't even wait for confirmation because, well, Mads is probably not going to scam me because I know him, but also the amount is so low that if he should attack it, he would have to mount enormously amounts of mining power just to win 100 kronos, and that doesn't really add up. But it really depends on the amount. So if it's a Ferrari or a house or something, then I would probably still wait 6 blocks or something like that.
Yeah, but there was also the possibility of sending 2 blocks out in the network.
Yeah,
and that wasn't expensive computing to do.
Oh yes, it is, because the block has to be sound. It has to be it has to adhere to the rules, so it has to have the right difficulty and such. So you cannot just put out a block because it will be thrown away if it doesn't adhere to the rules.
So if you first made the first one, then the second one it would have been too far behind.
Yeah. So Mads?
What if nobody wants to confirm my transaction? Maybe I put too small a fee on it, nobody cares.
So the question is, what happens if Mads doesn't put enough a fee on a transaction, and basically it propagates into the network. All the nodes they relay it. Actually, some rules here, but anyway, let's just assume that it's sent out to everybody, and nobody minds it. Then eventually it will disappear. So the transactions that haven't confirmed are kept in memory by the nodes, and when they get rebooted, they lose it, right? So after some time, it will just vanish, and then you can send it out again. But you cannot. The problem here is though that the nodes they refuse to relay something that spends an output that they have in their memory pool already. So you cannot just do that rapidly and then send it out again because they will kind of block it. So after a week or a month, then maybe you can try it again. But basically these outputs are kind of blocked until you successfully can send it out again. So, okay, a question at the back.
What happens when SHA-256 is broken?
Yeah. So the question is what happens when SHA-256 is broken? Well, then our entire financial industry will fall apart because they are using the same algorithm for their security.
It's easier to change for them than change the whole blockchain.
Not really. So, so first of all, when or if SHA-256 gets broken, it's very likely that that we will figure it out. That that there are some weaknesses. Like with SHA-1, some weaknesses were found, but it took a long time before real exploits could be figured out. Sorry?
SHA-1 don't have a real exploit yet.
Well, but yeah, so there are weaknesses, right? And we will learn about these weaknesses before it's really exploitable. But the thing is that we can change that algorithm. So we just need the majority of the network to agree that now we upgrade and use a different hash function.
But then the old blocks would still be hashed with SHA-256, and I would be able to read everything.
That is correct. And so basically he says that, well, that the old blocks, they can then be faked. But the thing is that the software contains, what do you call them, timestamps, or what do you call it, they have fixed points in the source code, which says that we all agree that 1 year from now, this block occurred at that time. So we have these fixed points, and they allow us to kind of say that no matter what happens, you cannot produce a chain that is longer than this, and then go this long back. But it requires, of course, that the nodes in the network, they upgrade and agree on this new rule. But they come all the time. A question down there?
How about the accounts, the IDs of the Bitcoin accounts? How do you make sure there are no duplicates, or how do you assign it when it's not centralized?
Yeah, so the question is, how do we ensure that Jan here and we don't create the same accounts, right? Because it's just random numbers, right? But the trick is that you have to make really sure that you have good random numbers, and you know, computers are not always good at that. But when you have a good random number generator, and you pick 32 random bytes, that is actually a large random number, and the probability of having accidental collisions is really astronomical. I don't remember the exact numbers, but when you do the calculations, it's something where you compare stuff to the number of atoms in the universe, and you know, big numbers, and it's really unlikely. So even if everybody in the world creates a new random Bitcoin address every second, then it will take 1 billion of years before there's a collision or something. It's really big numbers, but I cannot tell you the math off the top of my head. Yeah. Okay. So we're out of time. Thanks for listening, and remember to vote.